Welcome to the Mathematics Colloquium, and today it's a great pleasure to have Ajay Ramadoss from the Indiana University, Bloomington, and he's going to talk about representation, homology, homology and strong Macdonald conjecture.
Okay, so I thank the organizers, particularly Amrita and Shu, for inviting me here. It's nice to be here after almost 10 years. Okay, so what I'm talking about is joint work with Yuri Berest, my long-term collaborator, and Y. Kit Jung. Right. So in the first part of the talk, as a motivation, I'll talk about Macdonald and other identities, right? So let me begin with a very simple identity. So consider the following two-variable Laurent polynomial, k a positive integer, right. So one can ask what the constant term of this two-variable Laurent polynomial is, and that's a simple combinatorial exercise, right? So the constant term of this polynomial it's easy to see. It's the sum j running from 0 to k. So every time I have a y over x to the I and an x over y to the I, they contribute to the constant term. So minus 1 to the j, k choose j squared. It's not too difficult to see that this is really 2k choose k after some manipulations, right? So this is 2k factorial over k factorial squared. So the story then continues. In 1962, Freeman Dyson discovered without proof a generalization of this identity. So Dyson, 1962, without proof. He showed that if I take the constant term of the same kind of expression with n variables, or he didn't show but he observed. So this is nk factorial over k factorial to the n. He only observed this but was not able to prove this, right? Subsequently, in 1975, Andrews proved and stated and proved a quantization in some sense of this identity. So what he showed was the following. He said the constant term of the product right. So I'll explain notation in a moment. Right. So these expressions, and I'll say what they are very soon. So this is supposed to, this he showed was the q factorial of nk over the nth power of the q factorial of k. K q factorial to the n. So I now need to say what everything means here, right? So can people read the very last line down here? So where yqk is the following product. It's 1 minus y into 1 minus qy into 1 minus q squared y up to 1 minus q to the k minus 1y. So of course when q is 1, this becomes 1 minus y to the power k, right? And this epsilon ij in the formula, it's 1 if I less than j, q if I is bigger than j. And the q factorial of a positive integer m is the product 1 into 1 plus q into 1 plus q squared all the way up to 1 plus q squared plus up to q to the m minus 1. So you see that if you plug q to be 1, Andrews identity specializes to the identity Dyson observed. Okay. So then comes around 1982, there was Macdonald wrote this very famous paper called titled Some Conjectures on Root Systems, where he stated very far-reaching generalizations of Andrews' result. Okay, as a conjecture, where he conjectured very far-reaching generalizations of Andrews' result. So some conjectures on root systems. So I think 1982 in the Siam Journal of Applied Math or something like this. So in order to state these conjectures, I need to kind of put notation for the setup. So G is a reductive Lie group over the complex numbers. So later on, I'll stop distinguishing. I'll use the same notation for the real compact form of G. Right? There's always an equivalent. There's a real compact Lie group whose complexification is this. So I'll use the same notation. Little g stands for the Lie algebra of G. R, the associated root system. R plus a choice of positive roots. Right? Q, the corresponding root lattice. So it's the root lattice. So this is of course an abelian group. So I can take ZQ to be the corresponding group algebra of the root lattice. Now because the group operation in Q turns into multiplication in the ring ZQ, right, and it's an addition in Q. So it's conventional notation to write the element alpha in the root lattice viewed as an element in ZQ to denote it by e to the alpha. Right, so that's conventional notation. And then there is of course a constant term map from here down to the integers, which just reads off the coefficient of the group identity. Right. So under these, so there are two conjectures. So Macdonald had a Q conjecture and a QT conjecture. So I'll state different versions of. So Macdonald's Q conjecture first. So there is, so I'll write it in a form. So it's the product, it's the constant term of the product over the positive roots. And then I should say the product, I think J running from 1 to K. And then you have 1 minus q to the j minus 1 e to the minus alpha into 1 minus q to the j e to the alpha. Right? This was conjectured, and let me just check I have not made any careless mistake. That is correct. Right? So this is just a product I running from 1 to L, and I'll explain what L is. K di choose K. Okay. So I need to say what L is. So L stands for the rank of the Kartan. Right? And D1, D2, DL, these stand for the fundamental degrees of G. So let me just very briefly say what this means. It's a well-known fact that if I take polynomial G, invariant polynomial functions on G, right, that algebra is a polynomial algebra on certain homogeneous generators. Right? So in fact, L homogeneous generators, one of each fundamental degree. And that's the degrees of these homogeneous generators are the fundamental degrees. So it's a fact. Maybe. C P1 PL, degree of Pi is Di. Right? So another bunch of numbers that will play a role apart from the fundamental degrees are the exponents. So for each exponent is one less than the corresponding fundamental degree. So you also have mi's. It's convenient to sometimes write these numbers. Okay. So at least written in that form, if you put G to be GLN, you get Andrews. Okay. So it turns out that Macdonald's Q conjecture can be restated in different ways.
You want Q binomial?
It's a Q binomial. Of course, Q binomial. Yes, and then I need to say that n choose mq by definition is the Q factorial. Of course, you want Q binomial. Once you have Q factorials, you have Q binomial and so on. Okay. So it turns out there are different ways to restate this identity, right? It's not immediately, it's not a trivial calculation, but after some calculation, it turns out this is equivalent, some calculation, to the following identity, which is more symmetric. I'd write this in integral form. So I'll say integral over the real compact form of G, right, of the product J running from 1 to k minus 1, determinant of 1 minus q to the j at G dg. So this is the product I running from 1 to L, the product J running from 1 to k minus 1, 1 minus q to the k times mi plus j. So are people able to see this? Yeah. So the mi's are 1 less than the corresponding exponents. Okay. So here, what I mean by the left hand side is that you have G acting on the Lie algebra via the adjoint action, right? So I'm not working with a real compact form of G whose complexification is my reductive Lie group. And then I'm integrating with respect to the normalized Haar measure, right? And once and then I observe that for any element of the group, this determinant makes sense as it's determinant of some operator depending on Q, and therefore this determinant makes sense as a polynomial in fact in Q, right? So it's a product. So what I'm integrating is a polynomial function on Q, and by integral I mean I'm integrating the coefficients, right? It's a polynomial in Q with coefficients which are functions on G, and I'm integrating coefficients. So that's the integral version. So it's not immediate from there to there, but I think the details of this restatement are there in Macdonald's original paper. So Macdonald didn't stop over there. He proceeded. He in fact gave a two-variable generalization of this Q conjecture, which I will write in integral form. So Macdonald's QT conjecture which was that it was that the integral over G, now this time of an infinite product, and therefore no longer a polynomial in Q but a power series in Q, right? So the product n greater than or equal product over all n, I want the determinant of 1 minus q to the n plus 1, I believe. Yes. So it's a two variable power series in Q and in T. Like this. Okay. So it's the left hand side, the integrand is a two variable power series whose in Q and T whose coefficients are functions on G and integrating coefficient wise. So this, he said, is the product, or at least conjecturally, the product n greater than or equal to 0. So it must be 1 minus q to the n plus 1. Product I running from 1 to L, I can't miss that. Okay, 1 minus q to the n plus 1 t to the mi over 1 minus q to the n t to the mi plus 1. Mi plus 1 is of course di, but write it this way. Right? So this conjecture, if you put t to be q to the k, it specializes to Macdonald's Q conjecture. On the nose, because a lot of cancellations occur in these products. Okay, that's transparent thing. So these conjectures, both Macdonald's Q and QT conjectures, were proven by Cherednik in 1995 using the representation theory of double affine Hecke algebras, but I'll not be moving in that direction. Okay. Just for historical background. But apart from these, right? Apart from these, Macdonald had some had a bunch of other less known questions, and probably less known because they were a little bit less precisely stated. They're not stated as flat as conjectures here. Right? So to motivate one of these questions, so one of these questions is about an even analog of the Macdonald QT conjecture, and to motivate this, let me say the following. So consider Macdonald's Q conjecture. So Macdonald's Q identity for k equals 2, right? And if I do replace q by minus q, so let me write it in integral form. So if k is 2, k minus 1 is 1, so you just get that. And q is replaced by minus q, so there is a sign change. That's what it becomes. Now, this side is the Poincare series. So both sides turn out to be Poincare series of very well-known objects. No, series, in fact, polynomials of well-known objects. So the first is the Poincare series of the G invariant part of the exterior algebra on G, right? And the structure of this algebra well known. So there is this very famous Hopf-Koszul-Samuelson theorem saying that itself is an exterior algebra on prim G. So prim G exactly has one generator in degree 2 mi plus 1 for each multiplicity mi. So there is a Hopf-Koszul-Samuelson isomorphism. And this is the exterior algebra on prim G. And the Poincare series of that exactly the right hand side. So this special case of Macdonald's identity is obtained by taking Poincare series or of a very well known isomorphism, really computing the G invariant part of the exterior algebra on G. Right? Now in homological algebra, passing from odd to even is like passing from an exterior algebra to a symmetric algebra. So what is the even analog of this? That's also very well known. For convenience sake, I'll rather work with the symmetric algebra on G star rather than G itself. So you have, I can look at sim G star, which is polynomial functions on G, and I can ask for the G invariant part of it. So there is a restriction map from polynomial functions on G to polynomial functions on the Cartan, and G invariant polynomials. It's an exercise to show that they go to polynomials invariant under the Weyl group action under the Cartan. So W is the Weyl group, I should say. And then I can ask what happens if I take Poincare series on both sides. So if I take Poincare series, that becomes the integral over G dg over the determinant of 1 minus q at G. And the right hand side, there are multiple ways of writing it because it's a further fact that this is symmetric algebra or polynomial algebra on those generators. But the fact that generalizes or seems to generalize is the following. So I write it as 1 over the cardinality of the Weyl group, sum over each element in the Weyl group of 1 over the determinant of 1 minus qw, where the Weyl group is acting on the Cartan, and so everything makes sense over here. Okay. Of course, it's a fact that this is also equal to product I running from 1 to L, 1 over 1 minus q to the di, because of this generators being of fundamental degrees. So with this, I can motivate Macdonald's question. So Macdonald's question was whether there is an even analog of his Qt identity, the same way as this identity is an analog of even analog of that. That was Macdonald's question. So Macdonald's question: is there an even analog of the Qt identity? And conjecturally there is, and let me write it down. Oops. So it's a conjecture of ours. So it's Yuri Beresnay with other collaborators. Giovanni Felder, Sasha Petotsky, and Thomas Wilwaker. So the conjecture goes as follows. So it's a two-variable conjecture generalization. So such a thing, conjecturally, is the sum over all Weil group elements. Of course, I had to divide by the cardinality of W. So like that. Of course, if you put T to be 0 in this conjectured identity of ours, you recover what you get by, you recover the previous identity, which is known fact, right? So this, when you put T to be 0, gives you that one, right? And there is some evidence for this conjecture. So first of all, it's a theorem that conjecture holds for GLN. For all n, and therefore SLN as well. So general linear and special linear groups, it's at least at the level of these identities, it holds, right? So there is further evidence that I'll talk about at the end of this lecture. The question then is, where do such identities, be it Macdonald identities or this one, come from, right? And the two-word answer is representation homology. So I try to kind of say what this is about. Or how do, maybe I should, identities arise. And then one answer, maybe I should say. Representation homology. So that brings us to the second part of the talk, right? So of course I'm brushing quite a bit of the history, how this topic developed under the carpet. So I'm only talking about representation homology here in this talk in the context of topological spaces. So at least in this talk, I will not distinguish between a topological space, a pointed connected topological space, and a simplicial set model thereof, right? So it's a known fact through geometric realization that reduced simplicial sets model pointed connected topological spaces. Okay, so let X be a reduced simplicial set, meaning X0 is a point, single element set, maybe that's what you want. And then you know that geometric realization of X is a pointed connected topological space, and this is actually a Quillen equivalence, right? So one can simply forget about topological spaces and think of reduced simplicial set models. Okay, so I'll not distinguish between the two. So then, what is representation homology? One can look at, given this, one can look at this derived scheme called one should call the derived moduli space of G local systems on X. Okay, so there are abstract ways of doing this in derived algebraic geometry, but for paucity of time, I'll bypass that. Right? At least that's not how we stumbled onto this object. Okay, so maybe the one thing to note, or one fact, it's a theorem mainly by unwinding a bunch of abstract definitions, that this is actually a derived affine scheme. Okay. Okay. So what does this mean? So the category of schemes is the opposite category of the category of commutative algebras, right, or a field. So let's say K a field. So I'm always K a field. G, for now, an affine algebraic group over K. Not even, for now, I don't even need it to be reductive. I later require that. Right? Then one can talk about this. So the category of commutative algebras is the opposite category of the category of schemes. Likewise, so you can say affine derived schemes in the similar way. This is the category opposite to the category of simplicial commutative algebras. So when you say some object like this is a derived affine scheme, meaning it is represented by a simplicial commutative algebra. There's a simplicial commutative algebra that is rings of functions within quotations on this object. Okay, so meaning, so this is a really, so very strictly speaking, so there's the simplex category, right, delta, where the objects are these sets, finite sets, right, bracket n. So bracket n is set 0, 1, 2, 3, n. Morphisms are these increasing morphisms, not necessarily strictly increasing, right? So morphisms are generated by phases and degeneracies, right? So a simplicial object in any category is a functor from delta op to that category. So there are phase maps and there are degeneracies, and then you can write down an associated chain complex whose differential is the alternating sum of the phase maps and take homology of the chain complex. That's
so simplicial algebra is a functor
from this delta op to algebras, and simplicial commutative algebra functor from delta op to commutative algebras. So it's, what you should think of is you have for each n from 0 to infinity, you have a commutative algebra, and then you have phase and degeneracy maps between them. Phase maps go from n to n minus 1, degeneracies go from n to n plus 1. These are generally abstract, because even in the simplest case, right, once you kind of write down even a simplicial model of a circle, right, has lots of degenerate simplices. There are only there's only one non-degenerate 0 simplex and one non-degenerate 1 simplex, but any number of degenerate simplices. And so when you apply any functor and look at the associated simplicial commutative algebra, it will be big, but most of it will be degenerate. That's the thing. Okay. So what it means the following. So it means that O d rep gx is a simplicial commutative algebra, commutative K algebra. And then, as I said, you can make a chain complex out of this by taking in degree n, homological degree n, the degree n term of this, differential being alternative sum of the phase maps, and take its homologies. And that's what are called homotopy groups. So pi star O d rep, by definition, that's what homotopy groups are all about. So this is a graded commutative K algebra. And this is what I call or mean, by definition, this is the representation homology of X and G. Right? But now I kind of try to say how one kind of gets something like this more explicitly. Right? And so for this I do a digression. So still I am not kind of switching to G being reductive or anything like that. I do that very soon, but not now. So recall the following fact. So you have the category of groups, you have the category of commutative K algebras, right? And remember, G was an affine algebraic group defined over K. So this means you have a group functor going in the opposite direction, right? From given a commutative algebra, B, I can look at the group of B points on G. Right? This is a standard algebraic. That's what it means for an affine algebraic group, right? So it takes, G of B, really, if you want to define it formally, this is Hom in the category of schemes from spec B to G. So in the category of commutative algebras, goes like that. Right? That's a group. So it's a fact that this functor, so G has a left adjoint. That's a well-known fact. So you can even write it down, but I'll not do that here. So it goes in the other direction. So if we unwind this definition of what a left adjoint means, so that is to say, rep G gamma, which by definition is spec of gamma sub G, is the ring of functions on the scheme or variety. If you are uncomfortable with the word scheme, think variety. So affine scheme, really. parametrizing representations of gamma in parametrizing representations of a group gamma in G. So, for example, let's consider the case where gamma is a free group on some generators. Simply free group on n generators. So can anybody tell me what rep G gamma then got to be? If you have a free group on n generators, any representation of gamma into G simply determined by where each generator is sent to. Right? So therefore, this is simply, and there's complete freedom there, no relations, that's just as a variety G to the n. Which means this representation functor applied to this group gamma is just a tensor product. Just ring of functions on that, so that's a tensor product of n copies of OG. Right. The same fact holds for any free group. Free group even on infinitely many generators, you just have a tensor product of infinitely many copies of OG. Which you want to rigorously define, you can define it as a direct limit. Right. But so why is this good for us? Because out of any reduced simplicial set, there is a standard machine that allows us to construct a simplicial group which at every simplicial degree is like this, free. But not necessarily finitely, typically not finitely generated free, but free. Right? So the machine that goes is the following. So you have X a reduced simplicial set. I have this machine which is called the Kahn loop group of X. Okay, so all I'll say is that in each degree, this is like a free group on essentially the n plus 1 simplices of X minus some image of a certain degeneracy map. Right? But then the phase and degeneracy map is not too hard to write down, but one of the phase maps is hard to write down, but there's no point doing that here. Right? That's the situation. So there is such a simplicial group that's free in every degree. Right? The reason it's called the Kahn loop group is simply because if I forget the fact it's a group, simplicial group, view it as a simplicial set and blindly do geometric realization, you end up getting the base loop space of X, base loop space of the geometric realization of X. So that's why it's a loop construction. Okay. So you do this. Then what you can do is apply sub G to the Kahn loop group degree wise. Degree wise meaning in every simplicial degree. So you get Gx sub G. This is a simplicial commutative algebra over K, which in every degree looks something like this. It's a tensor power of some bunch of copies of OG. Maybe infinitely many, right? So it's a theorem that this actually is a model for this ring of functions on DREP. So this is a relatively, just to construct this doesn't require any knowledge of derived algebraic geometry, but turns out gives you that. So theorem of ours is that this representation homology is really just the homotopy groups of this particular very specific simplicial commutative algebra you construct out of a simplicial model. So next I'm going to state a bunch of properties of this. Right? So the reason why we call this derived representation scheme and representation homology is that the zeroth representation homology actually is something very familiar. So properties. One, that the zeroth representation homology of X is nothing but the ring of functions on the G representation variety of the fundamental group of X. So this is a gadget that people in geometry topology often study, right? Not theorists in particular. Right? So representation varieties of the fundamental group are quite popular. But the issue with representation varieties of fundamental groups is they are often very singular. So people try, some or the other trick of, mitigating these difficulties, either doing some resolution of singularities. So this can be viewed in some sense as some resolution of singularities, but in the derived algebraic geometry direction, right? But the point is that this does not depend only on the fundamental group. So that will be shown in the third property. So let me say This is also very important, though it sounds like a very trivial example. If I look at the circle is it's a KZ1 space, right? It has fundamental group Z and no higher homotopy groups. So a simplicial group model, I don't need something as big as Kahn loop group of the circle. I can simply replace it by the group Z in every simplicial degree. So if I do that, if I apply representation functor, I get OG in every simplicial degree, phase and degeneracies being identities. So there are no like higher representation homologies. So this is OG, meaning zeroth representation homology is OG. It's what you expect. And no higher representation homologies exist of the circle. They vanish. Okay. So this is actually useful because once you know this, you know what it is for wedges of circles. It's just tensor products of OGs. And then because these constructions commute with homotopy co-limits, you can, I'm not talking about this in this lecture in general, but just to briefly mention, you can compute representation homologies of all these spaces that can be obtained as push-outs of wedges of circles. So Riemann surfaces, length spaces, knot complements, like that. Right. So that can be done. But third, and this shows that representation homology doesn't depend only on the fundamental group. So if I take an n sphere, which is simply connected, so if it's simply connected, the fundamental group is trivial. So this is just a point and that's just the base field, nothing else, right? But this turns out to be something non-trivial. You get this graded symmetric algebra of dual Lie algebra put in homological degree n-1. So for S2 in particular, you're putting G star in degree 1. This graded symmetric algebra of G star in degree 1 means an exterior algebra of G star, where G star in degree 1, wedge 2 G star in degree 2, and so on. So you have that. So this shows that representation homology incorporates higher homotopy information as well. So this still is okay. So this is maybe car k, I should say, is 0. You want that, right? Because everything I said up to now didn't depend on characteristic, at least these abstract definitions, but this you need that. Okay. So the question, so now henceforth, for the rest of the lecture, I'm going to assume that case of characteristic 0, maybe even case real or irrational real or complex, essentially. And I want to assume G is reductive, right? So one thing is that these varieties come with group action. Therefore, the rings of functions come with group action. Same thing over here. So these things also come with group action, compatible with phases and degeneracies. So the representation homology comes with the group action. You can ask for the invariant part. Okay. So I'll talk about that in a moment. So let's assume X is simply connected, which is to say that its geometric realization is simply connected. Then there is this rational homotopy theory is well developed, right? So there are Sullivan models, Quillen models, and whatnot, capturing all the rational homotopy information about X. So can we recover the representation homology of X from rational homotopy theory? So that the answer to this question is probably the main theoretical result in our work. So under the above assumptions, right? Under these assumptions, so with the above assumptions, let Ax be a Sullivan model of X. So what Sullivan model means is that it's a cohomologically graded commutative differential graded algebra capturing all rational homotopy information. And that means its cohomology is the cohomology of X with coefficients in the field K. And then are people here familiar with Andre-Quillen homology? No, if not. So, but then, okay, so then if I take a free resolution, a semi-free resolution of this cochain Sullivan model will always be augmented because X comes with a map from the point and to the point, right? Therefore augmented. So I can take augmentation ideal of this, right, provided it's semi-free, and go mod its square. Then this if I take cohomology groups of this turn out to be rational homotopy groups of X dualized with some up to some shift in degree. So this way it basically captures all rational homotopy data. It's a very well developed theory. So from this, how to kind of recover, right? So let Ax be Sullivan model of X. Then I want to say from this cochain algebra, the representation homology of X. So here, the first statement actually doesn't require reductiveness of G. It is as it is. So it's just Chevalley-Eilenberg cohomology with degrees inverted of a certain DG Lie algebra, like that. Okay, where this stands for just the tensor product of G with Ax bar. So that augmentation ideal can be treated as a non-unital commutative algebra. It has a multiplication that's commutative, right? I don't care about its having a unit. It doesn't have one. This is a Lie algebra. So if I tensor the two, I get a differential graded Lie algebra. Okay, so this is in that. And let me just say what the brackets are, right? So this is the first part of the theorem. So psi tensor B bracket psi prime tensor B prime, just the bracket on G but with scalars extended, like that. That makes it. And then there is, if it's a DG Lie algebra, I can always do Chevalley-Eilenberg cohomology. That's very familiar theory. And then for G, this is where I use G reductive because I want to compare group action with Lie algebra action. So this turns out to be relative Chevalley-Eilenberg cohomology with degrees inverted of G tensor A relative to G, again with trivial coefficients. So it's just G invariant, Lie algebra invariant part of the first. Okay. So what this does is, at least express this unfamiliar representation homology, at least for simply connected spaces, in terms of something familiar, right? I mean, a much broader audience knows what Lie algebras are and DG Lie algebras are, and therefore what Chevalley-Eilenberg cochains or cohomology is. Okay, but this is both good news. Good news, therefore, is this fact. But bad news is that Chevalley-Eilenberg cohomologies of current Lie algebras are hard to compute. There are very few examples where this has been very explicitly done. Okay, so let me give two examples that are relevant to the Macdonald conjectures. So the first example is suppose X. So before examples, I need to even say, I need to describe two maps. So the question is how to study such gadgets then, given that this thing hard to compute, right? There are really two maps that come into play. Okay, so two maps to study The first one will turn out to be related to the Macdonald conjectures, the original ones themselves. So here I'm assuming X is simply connected, right? Then remember somewhere at the back of the story were invariant polynomials, homogeneous invariant polynomials on G. So given such a polynomial like this, what I can do is the following. So maybe I should say I can look at the reduced S1 equivariant homology of the free loop space on X. Right? So this is the other side of other gadget I want to look at. Now the free loop space on X comes with a circle action, right? And the circle itself, there are various covering maps of the circle, right? One-fold, two-fold, three-fold, n-fold, and so on. So these covering maps of the circle induce certain operators on S1 equivariant homology of the free loop space. And these operators have some common eigenspaces into which this decomposes. So this has a Hodge decomposition. So I just say it's just a fact that there is such a decomposition of this into the direct sum from 1 to infinity of certain Hodge pieces. At least on the right hand side, the Hodge piece for p equals 1, the lowest degree, this is just reduced homology of x. So I can look at constant loops, and that's how you get it. And then for p is 2, 3 higher, the Hodge pieces get more and more complicated. Okay, but now given such a homogeneous polynomial, one has, so this choice of notation is deliberate. These are like trace maps. So that's why I call them this way. So there is one from the Hodge piece with degree 1 less than the degree of the polynomial. You have such a thing, Lxk to the G invariant part of representation homology. So what I'm going to do is I'm going to take all the polynomials corresponding to fundamental generators of invariant polynomials, write these maps, and create and put them together. So recall that sim G star G invariance was polynomial algebra on a bunch of homogeneous generators. So degree of pi is di, and we had that mi is di minus 1. So I have the map trace pi or trace sub pi from the Hodge piece of component 1 less than di, so that's mi, to representation homology, the G invariant part of it. So what I can do is I can sum it all, and then I get something from the direct sum I running from 1 to L here, down there. So this is just a graded linear map. But this is a graded vector space, that's a graded commutative algebra. So you have automatically a map from the symmetric algebra of this. So this becomes a commutative algebra homomorphism. Okay. So the point is that even the left hand side actually somewhat computable for simply connected spaces in terms of the Sullivan model. There are you take Sullivan model, take certain Hodge pieces of cyclic homology of the Sullivan model, and that yields the left hand side. So it's actually computable thing. Okay. So this homomorphism is called the Drinfeld homomorphism, what we call it as the Drinfeld homomorphism. So the question that arises is, when is this an isomorphism? Because if it is an isomorphism, you know that G invariant part of representation homology is a nice graded polynomial algebra. So we have a certain sufficient condition, very simple sufficient condition for this. So question, when is the Drinfeld homomorphism an isomorphism? So partial answer is in the following theorem of ours, right? So if the rational cohomology of X is, remember X is simply connected, it's generated by one element right? So either freely or not freely, doesn't matter, or is generated by two elements. One even, one or freely generated, sorry. It's freely generated by two elements, one even, one odd. Then the Drinfeld homomorphism is an isomorphism for X. Is an isomorphism for X. So, example. Example 1, if I take X to be complex projective space CPK, then this theorem, so by the way, not only cohomology but even Sullivan model, right? So this is just Qx over X to the k plus 1. Degree X is 2. That's the cohomology of complex projective space. It turns out that the complex projective spaces are formal. So Sullivan models also are, you can take simply the cohomology. You don't need to do anything. Right? Then this homomorphism and isomorphism for CPK. So you have that Dirac's or symmetric algebra of Dirac sum I running from 1 to L of HS1 Mi CPK, and let's say we can work with complex coefficients. So this is isomorphic to HR representation homology of CPK GG, which can be expressed in terms of the Chevalley-Eilenberg complex relative one. So if I take weighted, so in this homologically graded situation, the analog of a Poincare series is weighted Euler characteristic. That's the right thing to do. And then if I take the weighted Euler characteristic of the left-hand side, this gives me the right-hand side of Macdonald's Q identity. That's what you get, written in integral form. And if I take the Euler, if I write down this Chevalley-Eilenberg complex using my previous theorem, and then take weighted Euler characteristic, this becomes the left-hand side of Macdonald's Q identity. Right, so this Macdonald's Q identity is just equating weighted Euler characteristics of two sides of this type of isomorphism. Right, so that this symmetric algebra turns out to be isomorphic to that Chevalley-Eilenberg cohomology. That was a special case of this strong Macdonald conjecture by Feigin and Hanlon back in the 80s. That conjecture was proven, not in this conceptual terms, but in a very ad hoc way by Fischl, Grozhnowski, and Telemann in an Annals paper in 2008. Right, so that takes care of, that's the most. So this is the most interesting example where it is generated by one element. Right? What about freely generated by two elements? So that's example 2. Suppose I take X to be Cp infinity times an odd sphere, and I put R to be positive to make it simply connected. Once again, these spaces are formal. So not only the cohomology, but even Sullivan model like this. It's QZT. Degree Z is 2, degree T is 2R plus 1. Right? So this exactly fits into the other condition. So once again, it turns out that this Drinfeld homomorphism is an isomorphism. So you have sim of the Dirac sum I running from 1 to L, this Hodge piece of Lx, so this specific x, yes, that's isomorphic xgg. And now if you take weighted Euler characteristics, any guesses which identity you get? You get Macdonald's Qt identity. So the left-hand side will give you the right-hand side of. So this gives me RHS of Macdonald's Qt identity. This gives me LHS of Macdonald's Qt. How much time do I have? Am I out of time already, or?
No, you have 5.
I have 5 minutes. So good. So if I take 5, I need 5 to 10 more minutes to explain the other part of the story. So the question is, how do even analogs of Macdonald's identity come? Right. So there is a similar such conjecture, but that doesn't involve this map, because there. So that's a slightly different story. So there is a map on representation homology that's defined even when X is not simply connected. So the second map goes as follows. So X arbitrary as a space. Then, okay, so you have I take T to be a maximal torus in G. I still want G to be reductive so that I can do this. Then, if I have a representation of something into T, it will of course give me a representation of that thing into G. And so the same at the level of derived representation schemes. So you have that. So at the level of rings of functions, you go in the opposite direction. Right, so these are now, remember, simplicial commutative algebras. And then it will turn out, as before, that G invariant part there is going to go to Weil group invariant part there. So if I take homotopy groups, so on pi stars. So remember, homotopy group simply means taking associated chain complex and taking homology. Right, so this gives a map from the G invariant part of the representation homology of G to the W invariant part of the torus representation homology. Right, like this. So this map I call phi G. So we call this the derived Harishchandra homomorphism. So maybe let me say that if X is an odd sphere, yes, if X is an odd sphere, odd simply connected sphere, up to Z2 grading, this just recovers for you Chevalier restriction map. This Chevalier, because if it's an odd simply connected sphere, you get really symmetric algebra of G star, put in even degree G invariance. The right hand side would be symmetric algebra of H star, Cartan dual, W invariance. Right? That's simply Chevalier restriction. That's what you get. Right? So this is a generalization of Chevalier restriction. So the question then is, when is this derived Harishchandra homomorphism or isomorphism? And our conjecture is the following, right? That this is an isomorphism. Phi G is an isomorphism. So of course, if the cohomology, rational cohomology of X simply, if the rational cohomology of X has one generator, this is known. Just singly generated, that's fine, right? Because either odd or even. If it's even and simply connected, then this is just Chevalier restriction. If it's odd, it's just there's nothing much. Either it's an exterior algebra invariant part or OG, and this is known. But the conjecture here is if phi G is an isomorphism, if this rational cohomology of X has two odd generators, yes, has two odd generators. So let me say what this means for, so example would be a product of odd spheres simply connected, for example. Right? So let me say that this conjecture totally open. At this level it's totally open, not even known for GLN. Right? At least for finite and not known. It's known for, I'll probably say what it's known for in a moment, but suppose I do this, right? Then you see that AX would be simply like QZT, degree Z is 2P plus 1, degree T is also 2Q plus 1, so like that, right? And if you apply this Chevalier-Eilenberg complex theorem, right, then phi G is induced on homology by the following map. So up to Z2 grading. Right. So if I'm only bothered about if I'm ultimately going to do weighted Euler characteristics, I'm only bothered about whether things are in odd or even homological degree. Right? Nothing else. So up to that, phi G is induced on homologies. Induced on homologies by the following map of complexes. So let me write it very explicitly. So I can do functions on G times G, right? That's degree 0. And then I make a Koszul complex. So to make a Koszul complex, I add some generators, namely a copy of G star in homological degree 1. And then I must put a differential. To say what the differential is, I must say what the differential is on generators. So I must say what kind of function d lambda is. So d lambda is the function which takes two elements of the group and applies the original linear functional to commutators. So on generators, there's one copy of G star here and two copies of G star in degree 0. G acts by adjoint action on all of them. So acts on the whole complex. Everything compatible with differential. I can take the invariant part. So that's up to Z2 grading HRXG. Right? It turns out, that's what it turns out to be after applying this theorem about Chevalier-Eilenberg. Turns out to be very explicit like that. And then I'm doing basically restriction. So I'm restricting to H. Because H is abelian, there is no differential. Differential becomes 0. You get W invariant. And conjecture. So conjecturally, the above map isomorphism on homology. Conjecturally, the above is a quasi-isomorphism. Right? Now, if I take weighted Euler characteristics on both sides, I end up getting both sides of the even Macdonald identity. So let's call this map star. So taking weighted Euler characteristics on both sides of star yields the even QT Macdonald. Macdonald again should be put, it's a QT Macdonald, again put in quotes because it's just an analog we conjectured earlier. Right. So regarding further evidence apart, so of course one piece of evidence for this conjecture, the fact that I combinatorial identity holds for GLN. Right. Another piece of evidence is, okay, so we know that this statement is true for, I'll say it precisely, GL2, SL2, and then you can pass to the limit, GL infinity, SL infinity, all classical Lie algebras in the limit, like that. So that's another piece of evidence. So this sort of does to this conjecture what Hanlon did back in 1986 to the strong Macdonald conjecture. So Hanlon also wrote a paper where he proved that Chevalier-Eilenberg statement in the limit as n goes to infinity. So that's what this does to here, and this is where things stand. Right? So this statement, of course, if you translate it in topological language, this statement is true for if X is simply connected, and then for GL2, SL2, GL infinity, SL infinity, of course, SO infinity, SP infinity, those groups. Right? So one last remark is what happens, because the original statement conjecture makes sense even if X is not simply connected. Right? So for X is S1 cross S1, let me just say it. G is GLN, right? David Nadler and Jiwei Yun, right, have a proof, but this proof uses geometric Lagrange, and it's up to a certain ansatz. So it's up to a certain unproven statement in that theory which they expect to be true but not been proven yet. So that is where things stand as of now as far as this is concerned. So I stop right here.
So this proof that you mentioned of Macdonald QT by identifying this side as something and that side as
the
well.
original Macdonald, not the even one. The original.
The original QT. Yes. So in a sense, what you have is a different proof which doesn't go through the Daha thing, is it?
Yes,
Would
it
that
doesn't
be
go
right
through the
to
Daha thing at all. No, it doesn't go through the Daha, because what we are saying is it doesn't go through the Daha thing at all. Actually, I know not much about Dahas themselves, right? So what happens is that the left hand, this representation homology is a certain Chevalier-Eilenberg complex. So what you're doing is it's a symmetric algebra explicitly on G star tensored with this polynomial ring on Z and T, right? At least the augmentation ideal thereof, and then G invariance. So you can write down its Euler characteristic. It's literally that integral that you get in the QT Macdonald identity, And then the other side is the symmetric algebra on some direct sum of Hodge pieces of loop things. One can compute that side very explicitly. So it's explicit symmetric algebra on explicit generators with explicit degrees. And so you get the right-hand side if you take weighted Euler characteristics of the QT Macdonald identities. So no, it doesn't really know Dahas at all. But why? Okay, so the strong Macdonald conjecture, this 2008 paper of Fischer, Grozhnowski, Telsman, right? They don't talk of these homomorphisms in this conceptual way like we do, but they just say that this currently algebra homology is symmetric algebra on certain explicit generators, and they give it. Right? That proof is kind of very ad hoc in some sense. So I don't know. It seems to me to be a specific machine invented specifically for solving or computing that particular currently algebra homology and so on. But no, it doesn't involve the Dahas at all.
Yeah, I see. Okay. So just another follow-up there. So this FGT paper you're talking about, I don't understand head or tail of it, but one of the things they keep saying is failure of Hodge decomposition, whatever that means. Is there, meaning Telemann or Gronowski is very fond of that. There is some failure of Hodge decomposition somehow is the thing
this is that they do some. They have some analytical operators with which they are operating. No, I don't we just took the result. Like okay, that this currently algebra homology, this symmetric algebra on certain generators, and used it. So it so happened that these homomorphisms we wrote down we can actually compute because they are expressed in terms of certain Chern-Simons classes on certain DG algebra. So we just computed it explicitly to these cyclic classes and landed up getting exactly those generators which they said. Then we could apply the result. Yeah.
Any more questions?
No, we wish to understand this Fischer, Grozhnowski, Telemann more. I don't know whether those techniques can be used to apply for this conjecture. This conjecture on the Lie algebra side, nobody knows apart from what we did. And on the group side, for S1 cross S1 for GLN, they claim using geometric Langlands, which we don't understand, and that too modulo something unproven in that theory. So somehow suddenly kind of found ourselves in deep water, so to say.